Let's take a look at the official definition for the inverse of a square matrix and think about what it really means. Given an n by n square matrix, A, this part tells us that we can only find the inverse of a square matrix. Now back to the definition. If there exists another n by n square matrix, A inverse, so the if in this part of the definition tells us that only some square matrices will have inverses. And back to the definition, where A times A inverse equals A inverse times A equals I sub n. Aha! This indicates that the multiplication must be commutative and that the product must be the identity matrix. So now we can complete the definition. Then we say that A inverse is indeed the inverse of A. And we can actually say that A inverse and A are inverses of each other. Using this definition, we can determine if two n by n square matrices are inverses of each other. For example, suppose we're asked to determine whether the matrices A equals row 1, 1, 3, negative 1, row 2, 1, 4, 0, row 3, negative 1, negative 3, 2, and B equals row 1, 8, negative 3, 4, row 2, negative 2, 1, negative 1, and row 3, 1, 0, 1, are inverses. Well, the definition requires that we check whether or not AB equals I and BA equals I. If so, then we will have met the condition that AB must equal BA and both must equal I. And we'll be able to claim they are inverses of each other. Conversely, if either AB or BA does not equal I, then the matrices are not inverses of each other. So let's check to see if AB equals I. Push pause and multiply these matrices together. Well, did you get the identity matrix I? If so, you performed the multiplication correctly, and we have that AB equals I. Now we need to check to see if BA equals I. Push pause and perform this multiplication as well. Did you get the identity matrix again? If so, you obviously have great matrix multiplication skills. And now we can claim that AB equals BA equals I, which means that A and B are indeed inverses of each other, i.e. A equals B inverse and B equals A inverse. All right, let's do another example. Determine whether B is the inverse of A given that A is equal to row 1, 7, 4, and row 2, 3, 2, and B equals row 1, negative 1, 8, and row 2, 2, negative 14. So first, we need to determine if A times B is the identity matrix I. Push pause and perform this multiplication. Did you get the identity matrix I? If you did, you better check your multiplication again. The product AB equals row 1, 1, 0, and row 2, 0, negative 4, which is not the identity matrix I. And since the definition of matrix inverses requires that both AB and BA equal the identity matrix I, we can stop here and claim that B is not the inverse of A.